sklearnmetricspairwiselinearkernel linear kernel. Description: the linear kernel function in scikit-learn calculates the linear kernel between two sets of vectors, which is simply the dot product of the vectors. This kernel is widely used in machine learning for tasks such as dimensionality reduction, kernel-based classification, and kernel-based regression. Inputs: X. This is a 2D array of shape n samples 1. N features representing the first set of vectors. Each row represents a sample, and each column represents a feature. Y. This is also a 2D array, but it can have a different number of samples than X. If Y is none, the function calculates the kernel between X and itself, i.e., it computes the pairwise dot products of all vectors in X. Outputs: gram matrix. This is a 2D array of shape n samples 1. N samples 2 containing the dot product of each pair of vectors from X and Y. Steps: it calculates the dot product of all pairs of vectors from X and Y. The result is a matrix where each element represents the similarity between two vectors. Metrics: the linear kernel itself does not have a specific associated metric. Its effectiveness is evaluated based on the performance of the machine learning model using it. Visualization plots: the linear kernel can be visualized as a heat map, where the color of each cell represents the similarity between two vectors. Fine-tune parameters: none. The linear kernel does not have any tunable parameters. Uncertainty methods: none. The linear kernel itself does not have uncertainty associated with it. Uncertainty is usually handled in the context of the machine learning model using the kernel. Challenges and fixes. Challenge 1: high-dimensional data can lead to numerical instability, making the dot product calculations unreliable. Sample use case: when dealing with datasets with a large number of features, the dot product calculations might become prone to rounding errors and other numerical issues. Fixes: feature scaling. Scale the features in the input data using techniques like standardization or normalization. This helps to reduce the magnitude of the dot product and improve numerical stability. Challenge 2: the linear kernel can be sensitive to the scaling of the input data. Sample use case: if features in the input data have significantly different scales, the linear kernel might give more weight to features with larger scales, potentially leading to biased results. Fixes: feature scaling. Scale the features in the input data using techniques like standardization or normalization. This ensures that all features have a similar scale, preventing the kernel from being biased towards features with larger scales.